In the last video, we looked at the geometric representation of vectors, and on this one, we want to talk about the algebraic representation of vectors. In particular, we're going to see there's great overlap in the language and notation between points, vectors, and complex numbers. So, for example, on the picture we have here in the yellow, we could think of this point as being the ordered pair xy. We could maybe call the origin, which is often called just point O, so I'm going to call that O. Then we could say that this vector OP, starting at O going to P, would be, and then we use these angle brackets, these kind of pointy brackets, and we could write that like this. So that's the vector OP. And it's what gets sometimes confusing is it isn't always done that way. So many books will leave it in that ordered pair notation with the parentheses, but from the context of the problem, expect you to understand that that's a vector. In most cases, these you can flow between them. So the way you think about it is kind of up to you or the context of the problem or whatever seems to make it the most sensible and the easiest to work with. And then in terms of a complex number, we have seen if instead of thinking these just xy axes, we could imagine that we've got our argon diagram again, where we're going to call that the real axis and the imaginary axis, and our complex number then is going to be x plus yi. So the x is going to be that real part, and the y is going to be that imaginary component. So these are all interchangeable there. And then we can do the same thing again in polar coordinates. So we can again think of this as a point, r comma theta, and we can also think of it as a vector. And so again, we can talk about that vector OP, and we could write that as r cosine theta, comma r sine theta. So again, that's given us those horizontal and vertical components, they're called, of that vector. Or we can think of it as a complex number. And there again, if we imagine now we're talking about real and imaginary axes, our argon diagram, then we can think of that as being our r cis theta again. That is, we've got that r times cosine theta plus I sine theta. Okay? So let's take a look at an example here. And we have a point A at negative 2, 4, and a point B at 1, 1, and we want to find the vector AB. So direction makes a difference here. So we're talking about starting at point A and going towards point B. And so what we do there then is, again, we find this vector using what we again call tip to tail. So we're going to take the coordinate of where we ended up, that's 1, the x-coordinate in the b vector, minus the negative 2, that's the x-coordinate of the a vector, comma, and then 1 is the y component or y-coordinate of point B, and then minus the 4. And so when we do that arithmetic, we're going to get 3 comma negative 3. So that is the component form of our vector AB. And again, I have written it with these, they're called angle brackets, these kind of pointy little things there, but you could also use parentheses and just understand from the context that you are talking about a vector as opposed to a point. The magnitude we have seen is going to be the square root of, and then we're going to get that 3 squared plus the negative 3 squared. So that's going to be 9 plus 9. That's the square root of 18, or we can call that 3 square root of 2. So there's the magnitude or length of our vector. And to find then the polar representation, the magnitude is going to, the magnitude is going to be our value of r. And if I like to think of it graphically, but you don't have to. It's not cooperating here. Let me see if I can get, there we go. For some reason it wasn't writing. So if we are at the point 3, -3, that's going to be down here. I think we can see that that's a 45-degree angle right there, hopefully. So we can call that the polar representation. We can call that r. So we can go r cis theta if you like, which is going to be 3 square root of 2. And we can call it cis a -45 degrees. Or if you prefer, and this is interchangeable, we could go with 315 if we preferred to get a positive angle. Okay, a new screen here. So we're going to talk here a little bit about some physics here. A force F of 10 newtons, that capital N represents newtons, and up here in the yellow, a newton is a measure in metrics. So using metrics, it's a measure of force. And so what I'm told is that that's how much force is required to bring a 1 kilogram mass to a speed of 1 meter per second in 1 second. There you go. Hopefully that makes some kind of sense. I don't know. So what we have then, if we imagine what's going on, I mean, you don't have to draw a picture here, but it might help the cause. So 130 degrees is going to be somewhere over here. So there's our 130 degrees, and the magnitude of that force is the 10. That's what the 10 newtons is telling us. So we have a magnitude of 10. That's going to be our r value, and we have an angle of 130 degrees. So in component form, our force vector is going to be r cosine theta and comma r sine theta. And so that's going to be our r, which is 10 cosine 130 degrees, comma 10 sine of 130 degrees. So that's our exact value. And if you punch that into your calculator, I believe that's going to become a negative 6.428 for the x component or horizontal component, comma 7.660. So there we have it. Now, next question is kind of interesting, and you can solve this nicely using a vector idea here. So we are looking for a point that is 2/3 of the way from A to B. So I think we can imagine that. We can visualize that we're looking for a point somewhere in this region right here. That's the point that's going to be 2/3 of the way from A to B. But what we can do is make it into a vector problem. So I'm going to, again, call the origin point O. And if we think of this then as vector OA, so you can imagine that. And then we can look at this as being vector AB right here. So what we have in going from this point that we want could also, as we flow between thinking of points and vectors, that could also be thought of as the vector OP. So if we can find the vector OP, then those components will be the coordinates of our point P. Kind of crazy. So looking at that then as a vector equation, then what we're going to get is that OP is going to be OA plus 2/3 of our vector AB. And once we get to here, this is pretty manageable because vector OA is going to be just those components, 0, 4 of the point A. That's going from the origin out to A. And then we're going to take 2/3 of, and now vector AB, remember we're going tip minus tail. So the 6 minus 0 is going to give us a horizontal component of 6. The 1 minus 4 is going to make that a -3. So in this carefully constructed problem, we have 0, 4 plus 2/3 times, we can do that, arithmetic. So 1/3 of 6 is 2, times that 2 makes that 4. And 1/3 of -3 is -1, times 2 is -2. And then finally we add those components. And so that's going to be 4 and 2. So our vector OP is given by 4, 2. That means our point P is going to be 4, 2. That is the coordinates of that point 2/3 of the way from A to B. So kind of a nice way to do that using vectors. Okay, hopefully that's enough to get you going on homework 8.